Thank you very much, and welcome back. And thanks for the invitation. It's always a pleasure to be here and to lecture. And so I would like to start with a short review of invariants of knots in this context of Heegaard-Floer homology. So, Okay, so the objects we would like to study are rational homology spheres, knots in rational homology spheres. For simplicity, I will always assume that the knots are null homologous. And the third structure we should pick is a spin C structure on the free manifold. So whenever you have such a triple, then the theory associates to it a fairly complicated algebraic object, and I would like to spend a little time explaining that. So what we'll take is what's called CFK infinity of K, and I will just abbreviate it like CK, is a finitely generated FU U inverse module. So this is the ring of Lorentz, and I will always pick the coefficient ring to be the simplest possible, the field of two elements. Finally generated FU module, which is a chain complex, and it has this distinctive property that the homology of this chain complex is very simple. It's just the ground ring. And so let me just very quickly remind you how this chain complex is defined. So first we take this triple and we represent YK by a Heegaard diagram with two base points. So double point. And then, as usual in this story, we take the symmetric power. So this is the genus G surface. We take the G-fold symmetric power, the products of the circles in the alpha and beta set, and the divisors corresponding to Z and W. And then we run this usual Lagrangian Floer homological machine. Lagrangian Floer homology. And remember that the generators of the chain complex are the intersection points. And for this particular chain complex, we only pick those which define the spin C structure as fixed before. And this gadget comes with some extra structures. Namely, all the intersection points come with a Maslov grading. So of the intersection points, they come with an extra grading due to the fact that we have two base points, which is called the Alexander grading. And so the differential will sort of respect that grading. It will drop by 1. It will disrespect the Alexander grading, but if we turn this grading into a filtration, then the differential will respect that. And also, such a module somehow doesn't have natural generators, but as we define, they do come with a natural generating set. So we fix a further grading, which is called the algebraic grading or J grading, which is just the exponent of U in front of a basis element. So we have, again, the differential will not respect this as a grading, but will respect it as a filtration. So at the end, we have a sort of scary sounding algebraic invariant. CK is a graded, bifiltered, finitely generated chain complex over FU U inverse. So this is the object we would like to study. And so here are two theorems which are relevant for our purposes. So the first just claims that this is a not invariant. So this is derived from work of Peter and Zoltan, and the initial idea also came from Jake Rasmussen, saying that the graded bifiltered chain homotopy equivalence type of CK is a not invariant. Said it differently, we might choose different presentations of our pair, the three manifold and the knot, and also throughout this Lagrangian Floer homology procedure we have to make additional choices like complex structures and such, and these choices will all influence the outcome. So as a bifiltered graded object you get something different, but if you start from the same triple, then the resulting objects will be sort of chain homotopic in a way that all the extra structures are preserved. And as I will show you in a few minutes, all the invariants you would like to study for knots, like the HFK hat or the HFK minus invariants, can be derived from that. So this is sort of the most general setting you can get from that theory. So let me define a further equivalence relation, which is just a simple generalization of concordance in that setting. So we say that Y1, K1, S1, and Y2, K2, S2 are concordant if there is a spin C homology cobordism, rational homology cobordism, from W from Y1 to Y2 and a smooth subset W, smooth submanifold W, which is an annulus, such that A is a cobordism from K1 to K2. So let me just try to do some, well, I will switch to the thick chalks. So we have Y1, K1, S1. So this line is symbolizing Y1, the two dots are the knot. And we have another one, Y2, K2, equipped with a spin C structure S2. And we are requesting the existence of a four-manifold W, which is sort of interpolates between the two ends. It doesn't have rational homology. And there is also an annulus, which is somehow crazily embedded, but C infinity, which sort of interpolates between K1 and K2. So we would like to understand not only individual nodes, but somehow equivalence classes of concordance classes. The advantage of this equivalence relation that it turns these objects into a group. So equivalence classes form a group, which I will denote by this script C sub Q. And I just remind you that the operation is the connected sum as addition. And the unit element is just the sphere, the unknot, and the unique spin C structure on S3. And so this is an abelian group, and this is one of those notoriously complicated and poorly understood groups in low-dimensional topology. Notice, okay, I will leave the lectures. Just push it up there. Yeah, whatever. Notice that there are maps between or good old concordance groups. So recall that C is traditionally the concordance classes in S3. And so with this notation, we have two homomorphisms, maybe more, but two obvious homomorphisms from C to CQ. We can take a knot in S3 and send it to just the 3 sphere, the knot, and the unique spin C structure. That's a homomorphism, phi. And there is another equally easily defined homomorphism where you take the knot in S3, you consider the double-branched cover, which is now a 3-manifold, and it happens to be a rational homology sphere. Indeed, H1 of sigma k has the cardinality of the determinant of the knot, which is always an odd integer. So we can take this 3-manifold and consider the branch locus inside the 3-manifold. And since the first homology is odd, it admits a unique spin structure. So we just equip it with the spin structure. And it's not hard to see that this is also a homomorphism between groups. So it's sort of an interesting problem to understand what are the kernels, what are the co-kernels of such maps. And I guess, I'm not sure, but maybe Jan will talk about the co-kernel of a very similar map later on this afternoon. Not at 4, but at 2:30. Let me just mention that, for example, these knots, which are some generalizations of the figure 8 knot, they are all in the kernel of phi. So these are called rationally sliced knots. Somehow they happen to be non-sliced in S3, but if you allow a rational homology disk with a rational homology ball with S3 boundary, then they will bound disks. So this is a slightly more general notion. Okay, so fantastic. The question is, how do we get something out of this picture? I mean, how do we handle such invariants? It's complicated as it looks. And so let me just very quickly run through how to picture such objects. So presentation of CK, well, we will sort of use dots and arrows on the plane. And so this can be, so fix a generating set of CK over the field F. So we have infinitely many generators, and which are homogeneous, A and J homogeneous. And then take such an element and associate to it a dot on the plane by considering the two coordinates J and A. So what you would expect is a picture like this. You have a couple of dots, something like that. And of course, I didn't say that because I was stupid, but I didn't tell you how the multiplication with U action has the following effect. So it drops by 2, drops A by 1, and of course it drops J by 1. So when we multiply it with U, we are moving in this direction. If we multiply a generator by U inverse, we go to this northwest. So, no, northeast direction. So the entire picture looks something like that. We have sort of a starting pattern, and we just shoot it out in both directions. And then when we have we would like to picture the differential, where the differential of a generator is some linear combination of other generators where the coefficients can be picked from the base ring, which is just the base of the ring of Laurent polynomials. Then we the corresponding dots. So this is like a typical, and indeed this is the picture of the right-handed trefoil, as you would guess. And then it goes on and on. Okay, so how do we get invariants out of such an object? Well, consider the following construction. So suppose that D is a subset in R2, which is non-empty and not the whole plane. So it's sort of a non-trivial subset. And it also has this additional property that it's sort of complete in the southwest direction. So with the property that if AB is in D and prime is less than A and B prime is less than B, then also A prime, B prime is in D. So this is just to say that if you have one dot in D, so your set is something like that, but if you have one guy in D, then this entire southwest quadrant should be in D. So in fact, my original picture was incorrect. It should look rather like that, like something like this. Okay, so suppose we take such a domain D, and CD should be the subspace spanned by those F generators of CK for which JX, AX is in D. So such a gadget will not be a submodule, at least not an FU U inverse submodule, but this will be an FU submodule of A. Indeed, if you have one guy and you multiply it by U, then you should drop in the southwest direction, so it's also in D. And I didn't say that, but this will be also a subcomplex. It will be closed under taking the boundary. So plus it is also a subcomplex. Okay, so for any weird domain in the plane, we can define a lot of sort of subcomplexes. And so this is what we do now. So what do we do? Consider D with the extra property that the origin is on the boundary of D. So again, my original picture was not exactly correct as it was drawn. I'm only considering those domains sort of for which the boundary passes through the origin, and then take I to be the embedding of CD to CK. So I consider this as a submodule, and finally denote the set X, Y with the property that this is in D by dt. So this is just a translate of the domain by t. So if you add a little bit, then sort of you translate it up or you can translate it down. And now the definition of the epsilon invariant of this knot K. But remember, there is also the three manifold in the spin C structure. I'm just not writing them. With respect to D, should be just the infimum of those T's for which IT of C dt into CK into the homology is onto on Y. So we have to remember that this is a particularly simple homology, as I stated at the beginning. This is just FU inverse. So in every second degree, there is an F, and in all the others, there is 0. And we just pick one particular most convenient degree, which somehow depends on Y and S. And at the moment, it's not important how this number is defined. And we just take those domains, which sort of, we just take those for which this homomorphism will be onto. So we sort of wait. There are those guys which generate this homology at degree dys. So they are somewhere on the plane. And we just wait until my translate of the domain picks them up. And when it first happens, I record that number. And this is my invariant multiplied with -2 for some unknown reason. Okay, so that's an invariant associated to every domain. So somehow we fixed my triple, a knot in a rational homology sphere with a spin C structure, and then for every such domain, I associate a number. Is that fine? Okay, of course, this is a little bit too general, and so we can specialize to convenient domain. So let me just check. Yes, so let HT, S, to be this domain. So this is a half plane with such a weird slope, somehow like this. If S is between 0 and 2, then these half planes will satisfy my condition that it's closed under this southwest motion, and also obviously its boundary sort of contains the origin. So we have these planes, and we can run our previous idea and define epsilon of the knot at the point T to be just epsilon of K for this domain HT. Okay, so in this way we get a function which is defined on that interval. So this gives a function epsilon K from 0, 2 to R. So, okay, so let me just list a few properties of this function. So main properties. Okay. I forgot to say something, so let me just get back. So we have these CK for these three manifolds and knots inside and spin C structures, and we agreed that this is a knot invariant in the sense that if you have various choices, then they will be chain homotopy equivalent. But I didn't tell you what happens with these chain complexes if you have concordant knots. So this is a theorem I wanted to tell you earlier. This follows from work of Zemke and also Jen Hom in various formulations. So it says that if Y1, K1, S1 I2, K2, S2 are concordant, then CK1, I will just drop all the other decorations, and CK are locally equivalent, which just means that, so if the knots are the same, then there is a chain homotopy equivalence. Well, if they are only concordant, there are still maps between the chain complexes, but we require less from them. And this is what I would like to spell out. So there is a map from CK1 to CK2, and from CK2 to CK1, both respect the grading and the bifiltration, but they are not chain homotopy equivalences, but sort of retain a little bit of those, such that F star and G star are isomorphisms on H star CKI. So they sort of don't match the two chain complexes as they are with the chain homotopy, but at least they induce an isomorphism on homology. This property turns out to be equivalent. Let me just continue it here. This is equivalent to the following, that there are other chain complexes, A1 and A2, such that CK1 plus A1 and CK2 plus A2 are graded, filtered chain homotopy. And their homologies are 0. So this phenomenon is called like stably equivalent. So the two chain complexes are not the same, not even chain homotopy equivalent, but if you add some mysterious but carrying no homology extra chain complexes, then they become the same. And this is the property which is very convenient to prove that these objects are actually concordance invariants. So let me just list a few properties of this Upsilon. So the first is that Epsilon K is a concordance invariant. And this is sort of the easiest to see because, so if you have two concordant knots, then this property tells you that their chain complexes are very closely related. They are almost chain homotopy equivalent. There is this annoying A1 and A2. But if you notice, the definition of the invariant is phrased in terms of the homology of the chain complex. But it sort of splits, and the second part just contributes nothing to this side. Definition doesn't change if you replace CK by this one. And of course, the two are the same. So if you replace it by this one, and then you just erase A2. So that's sort of obvious. And then I would like to tell you some more properties. Which are the following. Okay. So this holds for every D. The next one is that function of T, remember these are the guys where half planes as domains, is a piecewise linear continuous function of T. So this is sort of nice. I will give you a few examples. And the next one is that if we take the connected sum, then it just turns into an ordinary sum of these functions. So these are for knots in S3. And no, that's okay. And if you take the mirror, then it just picks up a negative sign. So these are sort of nicely behaving under the group operations of this concordance group. And what else? So these can be computed for torus knots. So let's write down for torus knots, there is an inductive formula which tells you the following, that if P is less than Q, then the Epsilon invariant of PQ is the same as the one of PQ minus P plus T P plus 1. So somehow for torus knots there is an inductive way to compute them. And so let me just make one more. This is a result of Feller and Kritsatovic, who, as I heard, sadly left mathematics by the time we all learned how to say and spell his name. So it's pretty unfair. And so as I alluded to, this function is piecewise linear and continuous. So we can talk about the points where you have a break of this piecewise linear function. And for example, for the n plus 1 torus knot, the first breaking point is at 2 over n. So having said this, for example, this property immediately shows the following, that a simple corollary is that these torus knots are linearly independent in the concordance group. So we always say that this is like an infinitely generated group. Of course, you know, there are many ways to show that. And for example, it's also known that all torus knots are linearly independent. But this property immediately tells you that the T and n plus 1 torus knots are linearly independent. Since if there is a linear dependence among them, then this combination of torus knots should have the Epsilon invariant constant 0 as the unknot does. But there will be a greatest n among the linear combination, and this will bring a breaking point at 2 over n, which cannot be compensated by any other functions. So it just survives. So it's a constant 0 with a breaking point at 2 over n. There are many more of these linear independence results, so I would like to show you a few. So one more is that if K in S3 is an algebraic knot, then the change at the breaking points at 2 over P and at 4 over P happen to be equal if P is at least 3 and odd. This is a result of Wang. And using this property, he showed that there are knots which are linearly independent of algebraic knots in the concordance group. So you just have to find a knot which doesn't satisfy this equality. So this is where this is somehow the breaking at these 2 points. And so P is any odd integer at least 3, and it just relates to breaking points. Maybe those are 0. It can happen. And so if you take iterated torus knots, some of them, many of them will be algebraic knots, but some of them will not. And they will violate that equality. So this is a way to show that they are not concordant to algebraic knots. And along the same line, there is a definition of Alfieri showing that the following set of knots, let me just take my glasses. So -2, -3q pretzel knots where q is at least 7 and odd is not concordant to a sum of algebraic knots. And the ni's are positive. And the significance of this choice is that actually these knots do pass this test. So from Wang's obstruction, they could be concordant. And the reason I brought it up, because it's sort of an interesting idea. So the idea of the proof is that consider the domains D, which is given by this equation. So these are our familiar half planes, but take dA to be D intersection with I less than A. These are sort of half planes, and these guys are truncated half planes. And then you can get an invariant eta out of this story by considering the following. So define eta of k to be the infimum of those A's where the epsilon invariant associated to D is equal to the epsilon invariant associated to dA. So somehow you can play the game of like comparing the various domains and the various epsilon invariants and so come up with numbers which might detect something about your knot. And this is exactly what Antonio used to show this non-existence of the concordance. There are a number of further variations which I might not go into. For example, a further result I would like to note, I would just mention that a further result along similar lines is that you can ask when are differences of torus knots concordant to alternating knots. So the epsilon invariant of torus knots is sort of fairly nicely understood. What happens with alternating knots, they have a very simple behavior in this theory. So the fact is that if K in S3 is alternating, then epsilon is particularly simple. It looks like this. It has a single breakpoint at 1, and the height of this tent can be also determined. This is just the signature of the knot over 2. So, you know, if you have a simple-minded invariant, you can be sad or you can be happy. I mean, you can be sad because it doesn't tell you much, but you can be happy because it sort of characterizes this class of knots. And so this is mainly the idea of being able to understand what differences of torus knots can be concordant to alternating knots. Let me just give you the statement, and then I would like to give you an explicit calculation in some cases. So the theorem, which is of work of Paolo Aceto and Antonio, says that if T PQ minus T P prime Q prime, so the difference of two torus knots, is concordant to an alternating knot, then we have three possibilities. So it can happen that the two knots are the same, so they are actually concordant to each other. So P is the same as P prime Q prime. Or it can happen that this guy is an alternating knot itself, or P equals P prime equals 2. These are the only alternating torus knots. Or, and what you would like to say is that there are no third cases. Unfortunately, there is one case left. Some specific torus knots. It's not so interesting at the moment what these are, and you would like to understand how to exclude these. So that's not done yet. The technique is sort of interesting how you get such a result. You play the game with these Upsilon invariants, and there is an extension of these ideas where you are not only considering the map from the domain to the entire chain complex and see when it is surjective, but you tweak it along a little bit based on the fact that the homology is one-dimensional for the chain complex, and this is what's called a secondary Upsilon invariant, which is due to Kim and Livingstone. So you only need to put this into the game, and then you will get something, and there is this surviving family, and you would like to twist the theory a little more to exclude them. It's not yet. Okay, so let me sort of go through an example, which I will pick alternating knots, and then the theory tells you that alternating knots are too simple, and you cannot expect anything from them, but this is not absolutely true. So I will pick a family which is particularly simple. Consider, let me just put this down. Consider the family of 2n plus 1 torus knots. And let's do some calculation for these guys. Well, so green is the new blue. So now I will try to come up with a doubly pointed Heegaard diagram for those knots, and then do calculations and then deduce something. So here is my Heegaard diagram. So so this is my W and Z, and I will add 1, n plus 1, 2n, 2n plus 1, n plus 1, 2n, 2n plus 1, and so on, n minus 1. So what does this mean? So what I would like you to see is a torus, genus 1 surface, by identifying this side with that side, and the usual identification between these two sides is sort of twisted a little bit. So I would like to identify 1 here with 1 on the other side, n with n, and so on. So instead of taking sort of the usual horizontal identification, we do this sort of skewed identification, and that gives us, there is this red curve on the torus, which is sort of easy to visualize, and then and the green curve sort of goes around in a sort of semi-complicated fashion. And I claim that once you take this doubly pointed Heegaard diagram, the knot you should see is the torus knot 2, 2n plus 1. It's sort of easy to see that what you will get is actually a torus knot. You are able to connect W and Z in this picture by two strands, one crossing the green ones and the other one only crossing the red, such that you get a knot embedded on the torus. So it's a torus knot, and in fact it's exactly this torus knot. So from this picture we can actually identify the chain complex. So these numbers will just represent the intersection points between the green and the red. So I will denote them by xi. So xi is the intersection point corresponding to I. And so here is the, the chain complex. So these are the generators. And the chain complex looks like this. So we can identify the boundary maps. And I will say one sentence how. This is x2n, x1, and w and z. So we can identify sort of the entire Floer chain complex from this picture. Remember, what you have to do is to identify the intersections between the two tori, which happen to be circles now, and we have to understand the maps from the disk to the symmetric power, where G tells you which symmetric power you should take, but luckily G is now 1, so we don't have to take the symmetric power, we just take sort of the torus. So we have to identify holomorphic maps from the complex disk to this torus, and so I can show you where these are with the boundary conditions that half of the disk goes to the alpha curve and the other half goes to the beta curve. And so, for example, there is such a disk, or there is another one, or indeed there are these big disks. You know, there are many of those. In this rainbow you have n many such parallel half circles, and these will sort of determine these maps. The corresponding moduli spaces always contain a single point, and so I claim that this is the chain complex. I mean, in principle, there could be some other maps which you can exclude by very simple arguments. And so in my previous picture, these points are located here, and then the boundary maps can be identified with this descending staircase. Okay, and so these guys have special properties. These are the ones which have Maslov grading 0. So when we would like to compute the Epsilon function, so what do we have to do? We take a certain slope, we consider this half plane, and we put it until we pick up one of the generators in Maslov grading 0. So if the slope is like less than the bisecting one, then this is the dot we will hit first. So until we change the slope from 0 to this bisecting one to -1, we'll sort of see a linear growth of the slope. Once you have exactly slope -1, then all the points will be aligned. And then when you increase it a little bit, then this point will be the one you have to watch. So there will be one breaking point which will happen exactly at t equals -1. Let me give you another such chain complex. If you do it for the 3-4 torus knot, then you will get a slightly different picture. It will look like this. The 3 dots you have to follow are these ones, and you can see that somehow there are 2 breaking points, one here with this slope and one there, because for a while you watch when you reach this one, then that one, and then that one. So this is the reason why the Upsilon function of this knot will be not like the usual tent picture for alternating ones, but a little different. Okay, so so that's what we have. And now, well, it doesn't tell us much. this little argument tells us that indeed the Upsilon function is a tent-like simple function. And it will look like this. But I would like to prove the following lemma, that this set of Torus knots, P is prime, are linearly independent in C. Indeed, again, we know that very well. We know that all Torus knots are linearly independent, but we hope that you get a sort of simple proof. Of course, I should sort of emphasize that simplicity of the proof is not an absolute statement. It depends where you come from, you know. Like, what do you consider to be known and what do you consider to be simple? So, I mean, knot theorists have a much simpler proof of like considering the signature function. But once you accept all this, what I said, like these are invariants and this is how you have to compute, then the actual proof is a very simple calculation. Let me show you how. So let's T2n plus 1, we denote it by Kn, and then consider sigma Kn S. So this is the double. And this is the knot in there, the branch locus. And so here is a little proposition that, so what's the proposition? So, proposition, and this is part of a joint work with Antonio and Daniele, saying that CFK infinity of sigma Kn tilde S naught plus age is the spin structure. This is the twisting parameter you twist with the spin C structure to get your spin structure, is chain homotopy equivalent to CFK infinity of the torus knot inside S3, which is just 2n plus 1 minus 2h, absolute value. So it just says that, you know, when you go to the double branched cover, what you have is not one chain complex, but one chain complex for every spin C structure. But indeed, these spin C structures will produce you chain complexes of some related torus knots. And so from this equality, from this isomorphism, we can compute the Upsilon invariance for every spin C structure. I will not do that. I will concentrate on that lemma, and I will sort of give you a shortcut. So let's think a little bit about how this double-branched cover works. So we have this picture. Let me just sort of schematically draw. We have the alpha curve, we have some horrible beta curve, and then we take 2 points inside and we take the double-branched cover. This is a genus 2 surface. We have 2 alpha curves, alpha 1 and somewhere alpha 2, and we have beta 1 and beta 2, and over every intersection point we will have 2 intersection points upstairs. So xi down gives us ai bi upstairs, and I will follow the convention that ai is always in alpha 1 and bi is always in alpha 2. And I also assume that A1 is in fact And then B1 is an intersection of alpha 2 and beta 2. And by inspecting the picture a little bit and remembering how to compute double-branched covers, this implies that AI is also an intersection of alpha 1 and beta 1 once I is 1 up to n and 2n plus 1, and AI is in A1 intersection beta 2 if I is n plus 1 all the way to 2n. So there are these two types of intersections when you lift to the double-branched cover. This actually tells you how many intersection points you have upstairs, because you can mix the AIs with the BIs at will if they are of the same type, and they don't intersect if they are of different types. So you have n plus 1 square from here and square from there. Okay, so that didn't bring us very close to the conclusion, but here is a little fact, is that, so we take an intersection point upstairs, which is some AI and BJ, and it can be computed. It turns out that this is just the average of the Alexander grading downstairs. And I have to tell you what the Alexander grading downstairs are, and I meant to do that earlier, but now I will do it. So a simple calculation of how the Alexander grading changes, plus that it gives you the Alexander polynomial, tells you that the Alexander grading here is n minus 1, n minus 2, n minus 3, and so on, all the way to minus n. So what you see from this picture is that there are 2 points upstairs which can have Alexander grading n. There is one point which has Alexander grading n, and one which has Alexander grading minus n. So A and Bn is the only point which has A equals n, and A2n plus 1, B2n plus 1, the only point which has A minus n. And for all the other points, the Alexander gradings are less than n in absolute value. Okay, so let me just try to wrap it up. So the first observation is that CFK hat CK n Kn tilde in the spin is isomorphic to CFK infinity to 2n plus 1. That's sort of obvious. We just take all these homogeneous like A and B and generators upstairs, and whenever we have a connecting bigone downstairs, we can lift it, we take the double-branched cover, and it will be a connecting rectangle, so we just get exactly the same chain complex. So it's not like they are isomorphic. When you pick these choices, the two chain complexes are just equal to each other. There is an isomorphism between them. And so finally, I would like to argue for the concordance statement, for this one. So suppose there is a relation sum of ni t, sum of I don't know, alpha I t to 2ni plus 1 or 2 pi minus sum of beta j t to qj. This is concordant to the unknot. Then we would like to get a contradiction unless all these coefficients are 0. Well, we can just take, so this means that the double-branched cover, which is a horrible connected sum of length spaces, bounds a rational homology disk 4 manifold for which like so many of the spin C structures extend, and for all those spin C structures you have to have an equality of epsilon invariants to be equal to 0. S naught will extend. The unique spin structure will extend. And this gives us the relation sum of alpha I, pi minus 1 over 2, minus sum of beta j, qj minus 1 over 2 equals 0. So these two sides should be equal. And I claim that there is also a spin C structure, which is the spin on one side, and it's non-spin on one of these. Let's sort of put this aside to prove that this such a spin C structure extends. Then we have a contradiction, because since any Alexander grading in any other spin C structure besides the spin is strictly less than n, all their epsilon invariants are less than n in absolute value. So what you do when you substitute the spin with this spin C structure is that you keep one side intact, and at least one term on the other side is decreased by some unknown amount. But since all these coefficients are positive, you just ruin this equality. And I will leave it as an exercise to see that such a gadget exists, and I think this is a good point to stop. Yeah.
Theorem right there, a proposition that's about k to n. Those are these. Yeah.
Say it again.
The sigma. What is sigma?
Yeah, and it's a double-branched cover, and so the way you can prove such a identity is you have to compute these guys, and luckily.
Have you looked at kind of other Torus maps?
So no, these guys are particularly nice because there is a very simple grid diagram which represents them, and this is an easy computation. Well, it's a tiresome and boring, but theoretically sort of theoretically fantastic computation. And not this one. So you come up with a grid diagram of these guys, for these guys. And this is sort of a funny grid diagram. It's in a length space, and it has height 2 and very long, depending on n. And then you get an explicit understanding of the chain complex.
You were explaining that thing is a branch double cover.
Yeah, so I proved less, right? I didn't compute this. There is this shortcut of when you only want to get some invariant, some linear independence, then you don't really need to compute. What I wanted to get into is that somehow by understanding what the Alexander gradings might behave, or if there is a bound on that, this might be enough. Of course, there are a zillion other ways to prove the same lemma. So, but you know, for twist knots, we can do something very similar. Again, you can prove it in some other ways, and you know, maybe I was not completely correct here. I should say that it's work in progress. So you know, there are some other applications we hope are even more stunning than this one.
When CFK was a staircase, you sort of drew a picture suggesting that convex hull the staircase.
Yeah, I mean,
is there an analogous statement that's not there? Is there some set of generators?
I mean, this is what you have to do. You have to identify, so somehow it's slightly misleading. It was correct, but staircases have this fantastic property that each dot itself is a cycle. And typically this is not what happens. So, you know, you can have like the sum of these two elements is a cycle, and this will be a representative, and then this whole convexity story a little bit breaks down. But other than that, this is exactly how you compute the epsilon. You just take your imaginary half plane and you push it until you pick up not an orange dot, but a combination of orange dots, which is a cycle. And so, but other than that, that's the picture you have to keep in mind. Does that answer your question?
Yeah.
Okay.